Have you guys started waves at school?
No, we're doing it API until end of term.
Yeah.
We start it next term.
Okay. Not sure what these guys are coming or not, because I know they just finished a SAC.
Yeah. So what are we gonna do today?
I was planning to do waves, but I'm not sure whether these guys haven't done their special relativity set. Let's see what depends on if what they're going to
Yeah.
talk about. Not sure these guys are not coming. We'll give you 5 minutes. If they don't come, I'm going to cancel.
Yep. I'll call Monik.
Oh yeah, they're coming now. How's your set, guys? Vidura, Manik, how was the set?
Yeah, I did really well.
What about Vidura?
Yeah. It was good.
Hard questions?
There was this one question about it was like a weight on a spring, and it just asked where was the highest net force.
Oh, okay.
I said it was at the top of the like at the top of the dilation. Like, you know what I mean?
That means
When the spring is like least compressed.
least compressed, then you have only the mg. They ask, so they ask you for the net force on what? Net force on the.
Yeah, they just said the overall net force of the whole thing.
Yeah.
When's the highest net force?
Okay. Net force will be maximum when it's fully compressed or just about to compress. Yeah. Okay. Anyway,
And
now
for the explanation, I just read that there was only mg acting on the weight as negative k delta x is equal to 0.
yeah. So,
Only mg is acting on it.
yeah, when it's fully compressed, then you have F acting upward, the spring force, mg down. You should get the similar net force, but acting upward. Anyway, what do you guys want me to do? Shall we start waves, or you want to still finish it off special relativity?
We finish off special rel.
Do half. What do you think?
Yeah, okay.
Special relativity, we did the time dilation and length contraction, right? Have we?
Hey, Derek.
Yeah.
Because I've done my sack on this, is it okay if I like join back when we start doing waves? Because I've got a method sack this week, so I thought I could study for that.
Yeah, that's fine.
So could you like send me a text or something when you start doing waves?
Yeah. Maybe just give about an hour.
Yeah. So I'll join back in at 5:30.
5:30. Yeah.
Yeah. Thanks.
How far have you guys done? Tell me.
We haven't done much. We've just started on it.
Okay, maybe quickly go to time dilation then. Remind you, yeah. So remember the two postulates, yes? The two postulates. First one, this Einstein's postulate based on the Michelson-Morley's experiment. When Michelson-Morley's experiment shows that speed of light doesn't change. So then Einstein came up with the idea saying that the first postulate is nothing to do with the Michelson-Morley's experiment. He was saying that there is no absolute frame of reference. Like if you do a physics experiment, any inertial frame reference, you should get the same result. The first one was laws of experiment. Sorry, laws of physics are valid in all inertial frames. So reference. Do you guys remember what the inertial frame is?
Non-accelerating.
Yeah, inertial means non-accelerating frame. Non-accelerating frame. That's the first postulate. Second one, that's the one related to the Michelson-Morley's experiment. What he was saying is speed of light doesn't change. Speed of light remain constant. Okay, regardless of motion of the observer. Or motion of the light source. So the speed of light remain constant c. Yes, regardless of the motion of the observer, motion of the light source. Yes, when you say inertial frame, think about the constant velocity, not constant speed, constant velocity, or that object is at rest. Yes, things are moving on a circular path, they are not inertial frames. All right. So since the speed remain constant, we know speed is equal to distance over time. So this stays constant for any speed going close to the speed of light. Then these two need to be changing. These two need to be changing. Speed. So the space and time is no longer a constant. In classical physics, what we're saying is speed, the distance and time stays constant, doesn't matter which frame of reference you're looking at in normal classical physics. In classical physics, where are we considering slow moving object? In classical physics, where objects are moving relatively slow speeds, we consider space, that is means distance, and time. Is absolute, that means not changing, or absolute. Does not change. However, the speed is relative. Now, when the objects are moving at relativistic speeds, very high speed, close to speed of light, when objects are moving close to speed of light, the speed remains constant. Hence, the space and time should be relative. So when objects are moving close to speed of light, the speed remains constant. The space and time become relative. They're not absolute anymore. This is where time dilation and length contraction comes in. We went through deriving this time dilation equation, right? Last time? Did we or didn't? T equals gamma T naught.
I think we did a bit.
Huh?
A bit.
We didn't go through and deriving that equation, no?
I'm not sure.
Okay, let me just quickly go through it. Okay, time dilation. Okay, guys, dilated time is always longer. Dilation means bigger. Proper time. Derive the proper time. In the same frame of reference. Same frame of reference. Where observe it. Observe, make the measurement. The time measured of an event where event occurred in the same frame of reference, where observe make the measurement. Say for example, spaceship is traveling. It's traveling at very constant speed, maybe 0.93. So he's performing some sort of event. So he's rolling a marble and trying to find the time. holding a marble inside, trying to find the time to travel. Distance x. The observer is inside. The event is occurring in the same frame of reference as the observer. That makes sense? It's making the measurement of an event where observer is in the same frame of reference. So the observer here, observer A, measure the proper time. And there's a guy outside on the ground. He's trying to make a measurement of that guy's clock. He would measure, he was looking at that clock, he would measure, the observer B will measure the dilated time. Do you guys understand here the proper time and dilated time? The proper time is where you're making the measurement. The event is happening in your frame of reference. Okay, so dilated time is where the event is occurring in different frame of reference. The dilated time is always longer. Proper time. Yeah. Consider a situation where, say, put a train, very high speed train traveling. Very high speed train is traveling. It's traveling at V, so close to the speed of light. So there is an observer on the ground. Say observer B. That's observer A. He's conducting an experiment. He's sending a light beam from the ground. And there's timing, how long it takes to hit the ceiling. And then coming back. So he's measuring the time for one direction. So he's measuring the time to receive from P to Q. So the height, say D, he measures the time. So speed equals, that's a light beam, this light is traveling at speed of light. The speed is equal to distance over time. So we measure the time, we're saying time is equal to D over C. Or you can say D equals C T naught. Now from observer B's point of view, from observer B's frame, what do you see? You see that while the light is shining, the light is traveling. And then the train is moving, therefore light beam traveling forward and reaching back. That's what the observer B sees. So that means the train has traveled distance x during that time. So that's T. The light beam has traveled a distance AO. PU. X equals to V times T. Time measured by the observer B little t. So therefore, I can say the PO is equal to x squared plus d squared. Or PO squared, V squared, T squared. Okay, so the D, so we can say the time T is equal to PO divided by still the speed of light c. The idea is to find the relationship between C and T naught. Just square both sides. Since d squared, so from equation 1, And then you can get an expression for t. You divide everything by c square. Now this is what we call the Lorentz factor. Dilation factor. Or we call the Lorentz factor.
Sir,
Yeah.
Manik texted me to ask you to let him into the call.
Who's this? Ah, he's gone. Okay.
Manik.
Okay. What happened?
My laptop ran out of charge.
If you guys can't see this step, turn off the light. So basically your T becomes gamma TO. Is that clear what was writing here, guys? Vidura? Mani?
Yeah.
So dilated time is always longer. It's called the Lorentz factor. You can rearrange that if you take it to, so if you take it the gamma, so the gamma is that, If they give gamma, you can find the speed. It's a fraction of speed of light. Just rearrange that for me. Just rearranging that to that.
So what would V be?
What's that? V is,
What
the,
would V be?
v is the speed of the object, yeah?
Oh, okay.
Like this case, like a train. If you throw a cricket ball, if you throw a basketball, find the Lorentz vector. Maybe just text Manik, like we might not be able to start waves at all. Not Manik, but
I don't have his number or anything.
I'll find.
Monik did.
Yeah, I'll text them.
Yeah, tell him. Because I don't think we can start because we had to go quite a bit.
Yeah, I've told them.
Okay. All right, you guys got the equation right. So get the gamma when you're targeting 0.7 C. You guys know that you don't need to put the C, yeah? It's just a matter of putting 1 minus 0.7 squared. The C's will cancel. What do you get for the gamma?
Do 1.4.
Okay. What's the lowest value for gamma you can have?
Is it 1?
Yes, 1. So gamma equals 1 minus 0.7 squared. The C cancels, so you don't need to do that. 1.4, yeah?
Yeah.
So if you look at the gamma versus speed, the graph, when it reaches the speed of light, your gamma become infinite. When v equals 0, the gamma become 1. So you need this graph because it indicates that if I want to travel or speed up until the speed of light, I need infinite amount of energy. Later on you will see that. It tells you need infinite amount of energy if I want to travel at speed of light. Example, some particles are coming, some tiny particles are coming on the ground. They're traveling a distance 10 kilometers. They're traveling quite high speed. Some particles. They're traveling at say 0.99 c. Okay, they're also on the ground. From the frame of reference of Earth-based observers. What do you get?
Wait, do we have to find the proper time of the particle?
No. I'm just asking from the Earth-based observer. This is speed equals distance over time. This is like when you consider the length contraction, you will understand that there's a proper length for the man on the ground. So just speed equals distance over time, because he sees the particles are coming 995, that speed doesn't change. He sees that it takes 10 kilometers. So how long these particles will take to reach the ground according to particles frame of reference? On the particles frame of reference. Who's measuring the proper time? Manik, who's measuring the proper time?
The particle.
The particles, because it's their journey. When they try to estimate the time, they are measuring proper time. If you know the gamma, you can work it out the time they take to reach the ground. So find the gamma. Okay. What do you guys get for the gamma? What do you get for the gamma?
I got 10.
10, yeah. Copy the number, not beta. So what would be the proper time? Proper time is always shorter. It's going to be 3.35 times 10 to the power negative 6 seconds.
Is it okay if I just quickly get to the bathroom?
Yeah. I'm feeling very tired too. I'm just struggling. Oh. You think you done okay with your sack?
Yeah, I finished like 15 minutes early as well.
Yeah.
Yeah.
Okay. Okay, now I'll give you another question. Maybe we'll do the length contraction, then we can incorporate both. Let's do length contraction first. Now, if you are observing the same event, two people are observing the same event, the time dilation and length contraction can't happen to the same event. Okay, say for example, the particles are moving, yeah, down. Particles are moving down. The man on the ground watching this, measuring the time for the particles to arrive. Okay, so the man will measure the dilated time. But then he will measure how far the particles are traveling. That's 10 kilometer is at rest in observer's frame of reference. but the particles are traveling relative to that. So particle feel like when they are stationary, actually mountain is moving other way around relative to them. You understand what I'm saying? So what I'm trying to say, when you're observing the same event, because your c, yeah, speed is c, so speed is v. Yes, the distance over time. Yes, distance over time. So we know that if you observing the dilated time, this dilated time, this has to be a proper length, because the other guy is observing, then contracted length and proper time. When you derive that equation, you will see that your d, which is the contracted length, is given by the proper length divided by gamma. That is given by, this is observed, like say for example, this is relative to the particle. This is relative to the man on the ground. In either case, the speed is the same. Speed is not relative. So therefore, d, which is d naught over gamma, if I replace that here, you will see you get the same equation as the other. Can you see that? Gamma t naught is your t. What I was saying is, if you're observing the same event, the same person can't observe the length contraction and time dilation. Then we can't say that then the speed is the same. Okay, just keep that in your head. The same way. Let's go and derive the equation. And also, because the dilated time is longer, when you are traveling on a spaceship for a trip, if you're trying to account for the time taken for a trip, when you are moving, your moving time is always slower. The moving time is the proper time, because you try to estimate your time. It's always slower, smaller. Smaller means your clock is ticking slowly. The clock ticks slowly. That's why the time is a lot lesser. Now consider this spaceship is traveling between 2 points. 2 points are on the ground. 2 points on the ground. The spaceship is traveling. There's observer. Observer A is traveling at speed v between 2 points. Now the observer on the ground, take a measuring tape. He measures that length between A and B. This guy measuring the time for his trip between A and B. Observe on the ground, this is just a PQ. Measures the distance between 2 points on the ground. Because that distance is in the same frame of reference as the observer. 2 points on the ground. So he said that the distance is L naught. And these guys trying to measure the time taken for the trip by the spaceship. He is moving at very high speed. So that he said that's going to be L. Now both are timing. Both people are timing. Observe A. Measures the time to travel between P and Q. So he says that the time between P and Q is equal to distance is L divided by speed. And then the observer B. Also measures the time. Between P and Q by the spaceship. So he's saying that, oh, that time is T. Distance was that. And V. So I can say the V is equal to L over T naught. Here is V is equal to T naught over T. We're talking about the same thing. So 1A is equal to 2A. I can say L naught over T. That's equal to that. These are clocks, by the way. Therefore, you can say L over T naught so the contracted length proper length divided by gamma. Contractor length is always shorter. Proper length is the length you measure where the object is at rest or in the same frame of reference as the observer. Proper length divided by gamma. Hey guys, keep in mind that length contraction happens only in the direction of motion. If you are traveling through a building, the contraction happening only in the direction you are moving. L naught is the proper length, because the PQ points are stationary relative to the observed P. You guys okay? Done?
What does it say since something equals 2a? Or
Where about?
top left?
Top left. Since 1a equals 1b, these two equations are same, yeah? 1a,
All right.
1a is same as 2a. These two equations are the same. Guys, okay? Once you're done, tell me how this. You guys done? What's still doing? Done?
Done.
Okay. All right. Now keep a note saying that the length contraction occurs only in the direction of motion. Motion of the wave. The body. Object. Example, if you have a building, this building has a circular window, building with a circular window, and the spaceship is traveling parallel to that. Mike, you okay? Yeah. So if the spaceship is traveling parallel to that, the spaceship would see, he would see that's observation of the spaceship. They would see the length is contracted, the building height would be still the same, say 30 meters or whatever, I don't know, just making up numbers. If that was 50 meters, you can see it shrunk the whole thing. That is still 30 meters. This has become, say, 25 meters. It's become like oval. Does that make sense? So the length contraction happened in the direction of the motion. The vertical height still remain the same. But it is, the width will be contracted. Peter and Jane. Okay. The star is 25 light years away from the Earth. The distance unit. If you travel with the speed of light, it will take 25 years. That's what the light years mean. 25 light years means if you're traveling at speed of light, it will take 25 years to reach the star. So how long Jane will take to reach the star according to Peter? How long Jane will take to reach the star according to Peter's frame of reference and Jane's frame of reference?
Would it be 22.5 years?
How long gain will it take to reach the star according to frame of reference? It should be longer, yeah? Longer than 25 years, because if you're traveling at speed of light, it takes 25 years. Now you are traveling slower than,
Would it be 27.8 years?
yeah, because you're traveling slower than speed of light. So 25 divided by 20.9. Is that clear, Vidura?
Yeah.
$27.77, yeah. So the distance is 25 light years, 25 C years. So your speed is 0.9 C. The C will cancel, you get 27.7 years. What about this guy? Gain's frame of reference.
Would the 25 light years be the proper length?
25 light years going to be proper length for whom?
For Peter?
For Peter, yes, because gain is traveling parallel to that, yeah. So 25 light years, that distance is the proper length for Peter. Proper length is the length where it is at rest relative to the observer. What is gamma? No units for gamma, okay? No units for gamma. No units for gamma. Okay, 27.7 years. That's this is the dilated time. So Jane will measure the proper time. T over gamma. You can do other way as well, find the contractor length and then speed equals distance over time. You can do that way as well. You should get the same answer. How far is a star? What's your sugar? Okay. What do you guys get it? Yeah, I gave the question.
Is it 10.89?
Huh?
I got 10.89.
So basically, we're looking for the contracted length. There is no over gamma. What's the gamma? I said 2 point something. $10.89, yeah, 10.9. 10.9 meters. Okay. Another question.
Is it meters?
I know that's in light years.
Oh, okay.
Light years. Now, question 4. While Jane was traveling, at point 9 C, she was sending a radio signal. Radio signal to the star. There's a detector. Now, what would be the speed of the radio signal? At the star. What is the speed of the radio signal received at the detector installed at the star? While this one is traveling at 0.9, he was sending the signal.
Is it just 1C?
Yeah. Should be always C, yeah? Speed of light remains same. It's not changing. Okay. We should quickly go through the muon or particles. Time dilation and length contraction. Muons. The muons are subatomic particles, very tiny. So this is the ground. The muons coming from outer space, not muons, actually the heavy protons or some heavy elements comes and collide with air molecules. Say protons or some heavy elements comes and collide with air molecules, atmosphere, and that's where the muons are producing. The muons are produced at upper atmosphere. It's roughly about 10 kilometers above the Earth. They're coming at very high speeds. Their speeds are similar to what we saw before. Quite high speeds. One problem, the muons are radioactive. They decay. They're radioactive. And they decay. They break down, they decay. Their half-life, you guys all know half-life, guys? The half-life of muons in muons rest frame is approximately 2.2 microseconds. Is micro. So, according to classical physics, the majority of muons will decay before they reach the ground. Before they reach the ground. But what's really happening is this is the real scenario. There are ample evidence to suggest that massive amount of muons actually reach in the ground before they decay. Very large number of muons are in fact reaching the ground. Reaching the ground before they decay. How do you explain that? How do you explain this? You need need to consider relativistic effect. Need to consider time dilation and length contraction. need to consider time dilation and length contraction. We'll do a calculation based on classical physics. Assuming that 100,000 muons starting the journey. Now, you purely look using classical physics. From Earth-based observers frame.
Where do they come from?
They're not coming from because the like heavy particles like protons coming from outer space, maybe sun or somewhere outer space. They come and collide with the Earth atmosphere, air molecules. During that collision, this is where these fundamental particles are producing. Muons are producing. During that collision, they generally generating about 10 kilometers above the Earth. Not very far, about 10 kilometers above the Earth, where they generate. The generated muons are coming very high speed. Muons are in the same category like a tau, muon, electron. They're all in the same category, leptons. They have a charge, but almost massless, like they have a very tiny mass. I think I attached a worksheet. I think it just shows how they generate. It's called muons. Maybe there should be a color picture somewhere. Okay, find it out. How long did they come to reach the ground? So 100,000 muons will begin the journey. Find how many muons will reach the ground. So here just a speed equals distance over time. Similar to what we got before. 10 kilometers. Something like that, yeah? I remember the number. 3.35 times -5. So if I want to write this one in microseconds, it will be 33.5 microseconds. Now, from radioactivity, you might remember this equation. The equation says N equals N naught half to the power, because half-life is how long it takes half the number of muons to decay. If I have 100,000, after 2.2 microseconds, it becomes 50,000. After another 2.2 microseconds, it becomes 25,000. After another 2.2 microseconds, it becomes 12.5 thousand. The little n. N means number of half-lives reaching the ground. So number of muons reaching the ground. N naught means number of muons, the initial number of muons. Initial number of muons. Little n means number of half-lives. Elapsed. So number of half-lives gone through fast. I'll get it on this side, yeah? Your n equals to the total time divided by half-life, one half-life. That would be 33.5 divided by 2.2. Both are in microseconds. (15.22) half-lives. So number of muons reaching the ground. Number of muons reaching ground. 100,000 times half to the power 15.22. If you use classical physics, that's all muons can reach the ground. Only 3 muons can reach the ground. But we see that the evidence shows that maybe 30,000, 40,000 muons reaching the ground. Not 3. Okay, because the half-life of muons was measured from muons frame of reference. It will be dilated in Earth-based observers frame of reference. It will be 22 microseconds. It will be 22 microseconds. The number of half-lives, so therefore the n value will be different. What's the n value we said? 1.5, 2 half-lives. Therefore, 34,000 muons will reach the ground. So that many times muons will reach the ground, according to Earth-based observer's frame. Does that make sense, guys? Now, how do you justify from muons' point of view? You should get the same number if the muons do the calculation. How muons going to justify that this many muons can reach the ground with?
Sorry, what?
Huh?
What was the question again?
The question was, if we use the time dilation, we can show that nearly 35,000 muons are coming to the ground.
Yeah.
We can apply time dilation from the Earth-based observer's point of view.
Yeah.
Then if that many number of muons come into the ground, then you should be able to justify the same thing from muons' point of view as well. The muon would be seeing that many muons come into the ground.
Yeah.
How do you justify from muons' point of view? Their time is not dilated because the 2.2 is measured from their frame of reference, their rest frame. So the 2.2 is valid for them. Manik, how do you justify? So these are the two scenarios they kind of ask you in exam mostly, from point of view of the Earth-based observer or point of view from the muons perspective. Something should trigger the bell. I remove my diagram. How far muons has to travel?
$10 kilometers.
10 kilometers from whose frame of reference?
The Earth.
Yes. But muons are the one moving. Then from muons' point of view, how far they have to travel? Gamma is 10.
Is it 1
Yes.
kilometer?
Yeah, muons' point of view, they have to travel only 1 kilometer. So the length contraction occurs from their point of view. The 2.2 microsecond is correct, but they have to travel only 1 kilometer. So basically 1000 meters divided by 2.2. The time takes to reach the ground is 3.35 seconds, microseconds. So still the half-life is 1.5. With respect to muon's frame of reference, the distance they had to travel will be contracted. So that's a contracted length. So they have to travel only 1 kilometer. (1,000 meters). Time to reach the ground, (9.5 times 3 times 10 to the power 8), which is 3.3 microseconds. Number of half-lives then, (1.522). Therefore, n would be same as before. We should be able to justify from both ends. That makes sense, guys?
Yeah.
Can I give you one question before you go? So this scientist doing an experiment in the lab, these tiny particles, not necessarily muons, they are radioactive. They travel distance AB. Travel a distance. Just give me a second, I'll just do a quick calculation. Okay. They can travel distance of 7.4. 0.75 nanometers. Before they decay. Okay, that's the distance they can travel. Okay, so that's the distance is 0.279 nanometers. I don't know, calculation's not right. No, so they can travel 0.2 meters, sorry, distance of 20 meters before they decay. So that's how far they travel before they decay. Okay, if the particles are moving, find their half-life. From muon's perspective. From muon's frame of reference, or particles frame of reference. The particles can travel a distance 20 meters before they decay. If the particles are moving at very high speed of 0.9 c, find the half-life of particles. Half-life of particles from particles frame of reference. That question is clear, yeah? I just gibberish a little bit there, but hopefully you understand. What do you get? Mike, what do you get?
I'm still doing it.
Okay. If you use the speed equals distance over time, that will give you the half-life in from the scientist point of view, scientist frame of reference. That will be the dilated time.
Is it 3.2 seconds? 3.2 times 10 to the negative 8 seconds?
That's correct. That's correct. So you find the dilated time first, speed equals distance over time, and then you divide that one by gamma. Your gamma should be whatever, 1 point something maybe.
I got gamma as 2.294.
Yeah, so 0.9 C, yeah.
Yeah.
That's fine. I actually, because you guys can't do that. If you look at your email, there is a one I attached, not this week, maybe a couple of weeks back. It's called time dilation. Can you give it a try, that one at home? Do you have any questions, guys, before we disappear? Next week, that guy again. Next week, we have to start waves at the same time. We just finished off the mass thing.
Would we be joining the class?
Yeah, because I started waves on that class now.
Okay.
So you are lagging behind the class lesson now. You can join in. I just did the basics like a wave equals F lambda. Haven't gone through much.
Will we be able to like catch up quickly?
Yeah. Now you mean?
No, not now. Like.
Yeah. It would be easier for me as well.
Okay. Do you have notes or something that we could use for waves?
I can send you the video recording.
Yeah, could you send us the video?
Yes. That would be good.
Okay.
Okay. Bye.
Thanks, sir.
Mhm.
Thank you.
Okay, see you guys.